Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all in today's session. Well, to access the notebook for today's session, you can access course page on my personal website arifpat.me. The other way is to download all the notebook files from the course GitHub account RFPUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.15 of the 6th module, Machine Learning, for the course titled Tools and Techniques for Data Science. Well, I think I have covered almost 30% of this module of machine learning, which is the application of artificial intelligence that gives the machine to the ability to learn without being explicitly programmed. Well, in the last session, we discussed different cross-validation techniques, and the title of today's session is Hyperparameter Tuning Using Grid and Random Search. So let's move on to the agenda of today's notebook. Before discussing today's agenda, let me give you a quick recap of what we have covered so far as per the machine learning life cycle that we discussed in our first session. Our journey started with the data acquisition phase, and so far we have explored and used many built-in toy datasets that comes bundled with Seaborn and scikit-learn libraries. We also explored real-world datasets that are publicly available in repositories like Kaggle, GitHub, UCI repository, and we also scraped data from web using Beautiful Soup, Selenium, and Scrapy. After data acquisition, we did data pre-processing and feature engineering to make our data ready to be fed to the machine learning model. And during this phase, we learned to perform 6 different tasks: detecting and handling outliers, missing values imputation, encoding categorical features, feature scaling, extracting and combining information. Well, during data pre-processing phase and otherwise as well, to understand the data visually, we have also made extensive use of libraries like Matplotlib, Seaborn and Plotly for exploratory data analysis. And then comes the machine learning model creation, training and the evaluation phase, where the main tasks were to choose the right estimator or machine learning model, train or fit the model on the training data, predict and evaluate the model on the test data. Well, so far we have just covered some basic regression models like linear, polynomial, ridge, lasso and elastic net, and some regression evaluation matrix for regression algorithms like mean absolute error, mean squared error, root mean squared error, R2 as well as adjusted R2 score. Well, in the last session we talked about different cross-validation techniques, which are statistical methods to evaluate generalization performance of machine learning models in a more stable and thorough way than a simple splitting of data into a training and a test set. Okay, so that was a recap. Now let me tell you what we are going to cover today. My dear students, the first model that we train and evaluate on a given data set is called the baseline model. Let's say that the R2 score of that baseline model comes out to be, say, 0.63, and the project manager has told us to do some magic to improve that score. Well, we can think of improving the performance of that baseline model from 2 perspectives: from a data perspective or from a model perspective, or maybe a combination of both of these two. Let me talk about the data perspective first. Over here, once again, there are 2 approaches. First is to collect or gather more samples as generally speaking, more is the data, the better are the results. And the second is, maybe we need to do more cleaning and pre-processing of our data. Maybe we need to add some relevant features if possible, and maybe there are irrelevant features that we need to drop from our data set. Well, I think we have done all these steps in our previous sessions, and of course you can improve the performance of your baseline model at your own using these data perspective. My dear students, today we will talk about as to how we can improve the performance of our baseline model from the model perspective. And once again, there are two approaches. First is to consider some other estimator or machine learning model, and second is perform hyperparameter tuning of the current model. And this is what we are going to do today, actually. And we will start with a detailed comparison between model parameters and hyperparameters. We will see as to how we can find different hyperparameters of our regression or our classification model with the specific emphasis on ridge regression model. And after having a clear understanding of hyperparameters, we will see as to how we can find the best hyperparameter values using these three techniques. First, we will do it manually using for loop by doing a simple train test split, and then by using k-fold cross validation. After having a clear understanding of this, we will do the same using two classes of scikit-learn, the GridSearchCV and the RandomizedSearchCV. So we have a lot to learn today. Let's start playing. My dear students, let me start by giving you a clear distinction between two very simple but confusing terms for many students, and they are hyperparameters and model parameters. Well, every machine learning model has its own set of hyperparameters, which need to be specified when you create the instance of the model before training. The value of alpha in ridge and the value of k in KNN are examples of hyperparameters. Moreover, the number of iterations and learning rate in gradient descent algo are also examples of hyperparameter. On the contrary, learning algorithm of a machine learning model learns the model parameters during the training phase. Every machine learning model has its own set of model parameters. For example, for linear and logistic regression, these beta 0, beta 1, beta 2 and so on are the model parameters that are also called regression coefficients. And the model parameters are of course later used for prediction. So my dear students, setting the right hyperparameter values while creating the instance of a machine learning model is very important, as it is going to impact the learning of the model parameters during the training phase. And choosing the best hyperparameters for your model is called hyperparameter tuning. I think I have made the two concepts clear. So now let me use this image that I have taken from the internet to give you an intuition of improving the performance of a model via hyperparameter tuning. It is just like controlling and adjusting the knobs of an oven to cook your favorite dish. Suppose that there are just two knobs. One is used to set the temperature and the other is used to set the cooking time. Say for the first time, you set the temperature to be 180 degrees Celsius and time to be 1 hour, but the chicken is not cooked properly. After a little bit of trial and error, you find that if you cook it for 1 hour at 200 degrees Celsius, your dish comes out exactly as how you want it. The same is the process that we will follow to find out the best combination of values for the hyperparameters of a machine learning model for a dataset. And my dear students, now a question that will come to your mind is, how can we find the hyperparameters of our specific machine learning model? Let's check out the hyperparameters of ridge model that we have studied in, I think, video lecture 6.13, and is preferred over linear regression when the input features are highly correlated. So let me first just import the ridge model from linear model module of sklearn. sklearn dot linear model. Let me import ridge, and let me say model is equal to ridge. And after creating the instance of the model, if you want to check out the hyperparameters of this specific model, you can call the get_params method on the model instance. So model dot get params. Let me execute the code of this cell. Great. So there is a whole bunch of hyperparameters with their default set of values being displayed over here. And this alpha seems familiar, which is a constant ranging from 0 to infinity that multiplies the L2 term controlling the regularization strength. And we have seen that if alpha is 0, we have non-regularized solution, and it is the same as using the linear regression model. Let me quickly give you a recap of the 3 regularization techniques using this image, and after that I will again fall back to those hyperparameters. And of course we have seen this in a previous session. We have learned that regularization are actually techniques that are used to calibrate linear regression models in order to minimize the adjusted loss function and prevent overfitting or underfitting. And the main idea is that it adds a penalty term to the cost function of standard linear regression. For ridge, it is lambda or alpha times the L2 norm, that is the sum of squares of magnitude of coefficients. This equation is shown in magenta color over here. For lasso, it is lambda times or maybe alpha times the L1 norm, that is the sum of absolute values of coefficients, shown in orange color over here. And if you want to get the benefits of both ridge and lasso, you can use elastic net regression. I hope it's clear. Let me move up again. So the hyperparameter alpha is quite clear. Remember, this alpha is the same as lambda mentioned over there. But what about the rest of these hyperparameters? For that, let me go up to the scikit-learn documentation. In the Google, let me write sklearn ridge regression. And this is the documentation page. Well, my dear students, just go through this documentation to check out details of the parameters of this function. And do note that sklearn call these parameters instead of hyperparameters, as we pass these to the ridge function just as the parameters of a normal function. For making you understand the hyperparameter tuning process, I will be tuning 2 parameters of ridge regressor. The first is this alpha, whose possible values can range from 0 to infinity. That multiplies the L2 term controlling the regularization strength. 0 value of alpha means no regularization. The other parameter I will be hypertuning will be this solver. That can be a string mentioning the name of the solver. That solver will be used in computational routines. That is a method to solve system of linear equations, actually, which we have seen before. This Auto is, if you specify auto as the value of this hyperparameter, the model chooses the solver automatically based on the type of the data. And this SVD uses singular value decomposition of X. This Cholsky uses Cholsky decomposition, and this LSQR use least square and is of course the fastest. And if you come down over here, you can read documentation of this ridge classifier as well, that converts binary targets to -1 and 1 and then treats the problem as a regression task. You can go through the documentation of GridSearchCV as well, which is a ridge regression with built-in cross validation. And my dear friends, make it your habit to check out the details regarding the hyperparameters of a machine learning model you are working on. Let me fall back to the notebook. Okay. Now that we have a fair idea about what are hyperparameters and how to check out hyperparameters of a specific machine learning model, the next natural question that will come to your mind is how to find the best combination of hyperparameter values for a specific machine learning model for a specific data set. Well, we will be using 3 techniques to find the best hyperparameter values for our model. And the first is, we will do it by trial and error using different values while creating the model, training it, and then checking out the R2 score. This is by hand. Then we will use a grid search and random search with the cross validation techniques. And of course, these are the generic steps that we normally follow for hyperparameter tuning. Please go through with these points. And I think enough of theory. Let's jump into code and do all this practically. Well, my dear friends, let me start by finding the optimized hyperparameters by trial and error. That is, trying every possible combinations one by one manually, which is of course not possible, but let's try that. And let me load our old friendly advertising dataset having of course 3 input features, specifying the company's expenditures in 1,000 rupees on TV, radio and newspaper advertisements, and the corresponding sales of items in 1,000 units. And this dataset has a total of 200 observations. Let us now do a train test split with 80% training and 20% test done. Okay, my dear friends, it is always a good idea to normalize the input features for every type of regression. And let me use the scikit-learn standard scaler to scale the data. That is, making the mean of the data as 0 and standard deviation as 1. So I have created the instance of standard scaler and I have called fit on xtrain. Then I have called transform on both xtrain and xtest. We have done it before as well. Great. Fine. Now let me instantiate the ridge model over here with default values of hyperparameters. Note that I haven't passed any hyperparameter to it. Train the model on xtrain, ytrain, and then you evaluate either using the R2 score method by passing it the y-test and the y-predicted, or you can use the score method of the model by passing it the x-test and y-test. Let's execute. Great. So we have got an R2 score of 0.856. 8586. Excuse me. Now let us adjust let us now specify the alpha and the solver hyperparameters. And let me give the alpha as a value of 1 and the solver as a value of auto, which is of course the default, and repeat the same code. Let me execute it. It gives us the same result, and this is very natural because alpha is equal to 1 and solver is equal to auto are the default values. And once you create a ridge model without any hyperparameter, it will use these default values. So the same R2 score makes sense. Let me try now. Let's say the alpha value of 1000 and the solver is auto. Let me execute. The R2 score is reduced to 0.22. Let me try alpha is equal to 100 and let's say solver is equal to least square. Let me execute. So now the score is 0.736, a bit better than before. Well, my dear students, setting different values of hyperparameters like this to get the best R2 score is very tiresome and manual. Another limitation is each time you do a train test split, you will get a different R2 score. Let me show you this second limitation using this piece of code. Over here, I have just gathered all the above code in one cell. You can see. The main point is each time I do a train test split, and since the shuffle is true, I will get different data values in the X train and Y train. Also note that while creating the instance of the ridge model, the hyperparameter alpha and solver has fixed values of 100 and LSQR, that is least square. Let me just execute this code cell and you get a score of 0.742. Let me execute again and again and again. So each time you get a different R2 score because each time the test set is different. So none of these R2 scores is a true representation of the entire data set. I hope this makes sense. And the solution to this is, of course, we should use cross validation. And we have covered it in detail in our previous session. Let me give you a quick recap of that as well. So this image describes the k-fold cross validation technique. We divide the data set first using the train test split. This 20% test data is also called the holdout data. This should never be used during training. We do a k-fold cross validation on this 80% training data set. And in this image, I have done a 5-fold cross validation by repeatedly splitting this training data into 5 train test sets. And this is called a validation split. So this fold 1 will give the R2 score by training the model on these 4 green splits and evaluate on this blue split, this validate portion. This fold 2 will give the R2 score of the same model but trained on a bit different green splits and evaluated on this completely different blue validate portion. And similarly for fold 3, fold 4 and fold 5. So we will get 5 different R2 scores or accuracies for the same model. And the mean of these R2 scores is the true representation of that model for those hyperparameters. Well, for every possible combination of hyperparameter values of our ridge regression model, we will repeat this. And the model with the best results will finally get evaluated on this holdout dataset, which the model has never seen before. And this is the code cell that do this job. So after loading the dataset, we are first doing our train test split as I have mentioned over here. So this is the train test split. After that, we are using the scaling of the data, and this is the cross val score method. which is a cross-validation method that trains and tests a model over multiple folds of a dataset. And the number of folds are, of course, specified by this CV argument. So this CV is equal to 5, means perform 5-fold cross-validation on this X-train and Y-train datasets. This first argument is the estimator, to which I am passing an instance of ridge regressor with alpha value of 100 and solver least square. By default, the scoring argument is the chosen model's default metric, and for ridge regressor the default is R2. You can mention a negative root mean squared error as well, and for classification you can mention F1 score as well. So this is the scoring matrix. And finally over here I am calculating the mean of the 5 R2 scores to get a single R2 score representing the evaluation of the entire training dataset. I hope this code makes sense. Let me execute. Great. So my dear students, these are the 5 R2 scores. 5 R2 scores, one for each fold over here. And this is the mean. Great. My dear students, if you see the code of this cell now, the main difference is over here. I am using a nested for loop to check out the best hyperparameters and without cross-validation. Well, in the initial few lines of code, I am just loading the advertising dataset, doing a train test split, and then scaling. Well, this alpha list is a list of 8 possible values of alpha. 1, 2, 3, 4, 5, 6, 7, 8. Yes, 8 possible values of alpha. And this solver list is a list of 2 possible solvers, least square and SVD. Now to check out which out of these 16 combinations, 8 to the 16, there will be 16 combinations, that is 1000 with least square, 100 with least square, 10 with least square, 5 with least square, and so on to 0.2 with least square, then 1000 with SVD, 100 with SVD, 10 with SVD, and so on to 0.2 with SVD, total of 16 combinations. So we're going to check out which out of these 16 combination of values this ridge regression performs best. And I'm using 2 nested loops. This outer loop runs 8 times, each time with a value of alpha from this alpha list in A. For each iteration of the outer loop, this inner loop runs 2 times with a solver, either least square or singular value decomposition. And inside the loops, I'm just creating an instance of ridge by passing it a combination of the 2 hyperparameters that I want to tune. Then I'm training the model on training data and evaluating it on the test data, and printing the, of course, R2 score. Hope the code is clear to you all. Let me execute this. Great. Well, these are the R2 scores for 16 different combinations of 8 alpha and 2 solver values. We can choose the hyperparameter values that gives us the best R2 score. Probably this 8, 4, 3. These are the best values. 8, 4, 3, 2, 6. You can choose any best value closer to each other. 8, 4, 3, 2, 8, 4, 3, 2, 6, 0. This is more or less same. And this is also same. Anyway, my dear friends, using simple train test split as we have done over here, there are 2 limitations. First is that the model evaluation is done on just this 20% of the data. Second is, once we finalize a specific combination of hyperparameters, we don't have any unseen data on which we can evaluate the final model. And of course, the solution to this is cross-validation. So let me do that now. Excuse me. So here is the same piece of code, but using cross-validation this time. The only difference is the code inside these for loops. Rather, the only difference is actually this line. Instead of instantiating the ridge model and calling fit and score method on it, I am using the cross_val_score method, which is performing a 5-fold cross validation on the training dataset, instantiating the ridge model for 16 different combinations of the alpha and solver hyperparameters, and each time it is returning 5 R2 scores of the 5 folds or splits. And finally, I am printing the mean of the 5 R2 scores. Let me execute it. Great. And from the output, once again, you can see that the best scores are coming up with an alpha value of, I think, 1 and least square, I think. Yes. Anyway, great job done. Well, my dear students, scikit-learn's model_selection module provides GridSearchCV class that does exactly the same thing as we have done above using the for loops, but this time using a single line of code. And the GridSearch is the simplest algorithm for hyperparameter tuning. As shown in this image, we divide the domain of hyperparameters into our discrete grid. For two hyperparameters, our two-dimensional grid is shown over here. The blue intersections, these dots, are the different combination of values. The GridSearch algorithm will train a model using every combination of these values and evaluate the performance of each model. Let me show you a code snippet that will use GridSearchCV to find out the best parameters. I hope this will be making sense to you all. The first line of code is actually importing the GridSearchCV class. The next few lines of code are loading the advertising dataset, doing a train test split, and scaling of the data using standard scaler. And over here, I'm creating a dictionary with parameter names as keys and their corresponding values that I want to check as values. Remember, if you want to check n hyperparameters, this dictionary will have n key value pairs to create an n-dimensional grid. But over here, I just want to check out for the learning purpose just two hyperparameters, alpha and solver. So this will be a two-dimensional grid. Okay, so this is the GridSearchCV method. I am passing it 5 arguments. The first is the estimator, which can be a regressor or maybe a classifier. Over here I have called ridge. Note that I have not passed any hyperparameter over here. The second is actually the param_grid argument. This parameter grid to which I am passing the dictionary that I have created above, that is params. The third is a scoring argument, which is R2 score in this case. This CV is 5 for 5-fold cross validation. And finally this n jobs parameter specifies the number of jobs to run in parallel. The default value is none, which means do not run the job multiple on multiple CPUs. I have used -1 over here, which means use all available processors. And after creating the instance of GridSearchCV object, I am calling the fit method on it, by passing it the X train and Y train, and then of course printing the best underscore score underscore and best underscore params underscore attribute of this trained object. I hope it was a good walkthrough of this code which makes sense to you all. Let me simply execute it. It will take a bit of time. Okay, so the best score is 0.891 with an alpha value of 1 and solver as LSQR, that is least square. My dear students, other than this best score and best params attribute, there are other attributes as well which are available to you now. You can check them out. Let me just print out the available methods and attributes which are listed over here. Let me just show you the gs.cv underscore results attribute. Great. So quite a bit of information given as our dictionary. You can see that this is our dictionary of key value pairs, mean fit time, standard fit time, mean score time, standard score time, parameter alpha, parameter solver, and so on. For a better visualization, we can change this dictionary to a pandas data frame. Let me just copy paste this and create a pandas data frame from this by saying pd dot data frame and just paste it over here. df is equal to, okay, great, lot of information. Well, the times to fit and evaluate, values for alpha and solver parameters, and since we have 5-fold cross validation, so score for each of the 5 splits is there: split 0, split 1, split 2, split 3, split 4, and the mean times and so on. Okay. And since our parameter grid has 5 values of alpha, I think 5 values of alpha are there: 1000, 100, 10, 1 and 0.5. 5 values of alpha and 2 values for solver. So there will be a total of 10 rows over here. Yes. 0 to 9, 10 rows. Great. I hope this makes sense. Let's just see the hyperparameter values. Let me just say df.lock and let me show all the rows, and let me show just this param alpha. Let me copy it and paste it over here, and let me show you the value of solver. Copy, paste, and let's check out the mean test score as well. We have the mean test score over here. Okay, I hope this is making sense. Let me just run it. Great. So this makes sense now. You see the best score is over here. Good. Well, my dear students, although it is good, but there are limitations of GridSearchCV. It is of course good as it performs an exhaustive search of all possible combinations to find the best and optimal set of hyperparameter values. But like no free lunch, it has its limitations. Let's suppose that we have a million of data points in your dataset and a bundle of hyperparameters and their values to be tuned. In such a scenario, the algorithm will become computationally expensive as well as very time consuming. I hope this makes sense. And the solution to this is RandomizedSearchCV. Well, my dear students, this RandomizedSearchCV is very similar to the GridSearchCV. The main difference is that instead of using all the points in the grid, it tests only a randomly selected subset of these points, as shown in this image. The smaller this subset, the faster but of course less accurate the optimization is. The larger this subset, the slower but more accurate the optimization is. Let me go through this piece of code that will do this practically. And of course the first line is importing RandomizedSearchCV class from the model selection module of sklearn. The next few lines of code are as usual loading the advertising dataset, doing a train test split, and scaling the data using standard scaler. Then I am creating the our dictionary with the hyperparameters that we want to adjust as keys, and the values we would like to try as the values of that dictionary. And instead of creating an instance of GridSearchCV, I am creating an instance of RandomizedSearchCV. And the first argument I am passing is the estimator. The second argument is param underscore distributions, to which I am passing the parameter grid as usual. The third argument is n underscore iter, which I have set to 6. This is the number of models to try. Instead of a total combination of 10, I just want to try 6 random combinations. Then we have the scoring and the CV and the end jobs. Great, already discussed. So after creating the instance of the RandomizedSearchCV object, I am calling the fit method and then printing the best score and best params attributes of this trained object. Let's execute the code. Great. We have got the best score and the corresponding hyperparameters values of the solver, which is SVD this time, and alpha, which is 0.5 this time. Well, anyway, my dear students, please do hyperparameter tuning on some other dataset, and do use lasso or elastic net model for practice for a crystal clear understanding of this very important topic of machine learning. In some future session, inshallah, we will use the same techniques to find out the best machine learning model out of many for a given dataset. And I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.